Ladies and gentlemen, good afternoon. We deal with fatigue testing of materials, and we deal also with notches. And in this talk, I would like to say some words about how we use average strain energy density for fatigue life estimation of notches. This is work of me. My name is Klusák, and my colleague Kamila Kozáková is my PhD student. And both we are from the Institute of Physics of Materials of the Czech Academy of Sciences. Well, first the outline of the presentation. After a short introduction, I will introduce the theory of critical distances, and especially how we use strain energy density in this approach. And then I will show how to determine the critical distances, and I will use them for fatigue lifetime predictions. This approach will be modified by stress concentration factors, and it will be, all this will be shown on examples of two materials, structural steel S690 and stainless steel 304. Well, you know that notches are components everywhere, and they work as stress concentrators and lead to crack initiation. So prediction of fatigue lifetime of notches is, let's say, evergreen problem, evergreen issue. And there are some famous names from Neuber, Peterson, Zdeněk Nessel, Dominic Legion, David Taylor, and Lucas Ismail, who are working still, or who were and are working on approaches how to assess notches. These approaches are called generalized linear elastic fraction mechanics, finite fraction mechanics, theory of critical distances, etc. And all these approaches somehow require the involvement of an evaluation distance. And on this distance, we usually evaluate axial stresses, strain energy density, plastic zone size, and so on. Today, I will talk about the theory of critical distances. Here you can see a notch in a specimen. The specimen is loaded in axial loading, and here is introduced line method of the theory of critical distances, where stress distribution is drawn here, and this stress is evaluated over some critical distance. Similarly, we can evaluate over this distance also strain energy density. The relation is here, and the original idea of the theory of critical distances is that the average stress over the critical distance is the same regardless to a notch type. With this assumption, it can be used for prediction of fracture or fatigue lifetime of notch components. We try to use both the axial stress, but also the strain energy density, because it can cover also influence of multi-axial stress and so on. So the first problem is how to determine the critical distances. Here I will show how to do it from strain energy density. We need some experimental data shown in this graph, and then we need stress distribution or strain energy density distribution ahead of, in front of the notch tip. Here it looks, this graph looks like SN curve, but it is not because this on the vertical axis we have strain energy density. Number of cycles of failure is here. The strain energy density is somehow proportional to the applied stress, so the graph looks very similar. And how to determine the critical distance? We say that the critical distance, you can see it here, the strain energy density averaged over the critical distance is the same as the average strain energy density for smooth specimen for particular number of cycles to failure. In this way, we can determine the critical distances, how they depend on a number of cycles to failure. Let me show it on an example. Here we have real SN diagram, fatigue data of structural steel of S690. These data were determined on ultrasonic fatigue system under high frequency and under this stress ratio. For each pair of notched and smooth curve, the smooth one is the black one, and the color curves and points are experimental data measured on the notch radii with the radius of 3 millimeters, 1.5, 0.8, 0.4, 0.2, and the yellow one is 0.1 millimeter. When we determine the critical distances, we get these curves, these dependencies of the distances on the number of cycles to failure. You can see that the distances depend on number of cycles of failure, but they differ also for different notch radii. And now when we take, for example, the green one, the green curve as a calibration curve, we can predict fatigue lifetime of other notches by means of the green curve. How it works? Not too well. You can see the predictions, which are the curves of particular notches, and the dots are still experimental data, and the predictions are not good for this case. These predictions are made from the green curve, so all these predictions are around the green dots. So we used a modification of the critical distances, and this modification is shown here, where for prediction we use this distance, and the original critical distance is multiplied by the ratio of stress concentration factors. This is stress concentration factor of the calibration notch, and this is stress concentration factor of the predicted notch. When we modify it, the prediction matches quite well to the experimental data. You can see it here. On the following slide, there is the original prediction, and now here on the right side are the predictions made by this modification. These predictions are made from strain energy density. This pair of graphs shows the approach from the strain energy density, and this one is from the axial stresses, similar modified approach. And you can see that the strain energy density in some cases gives little bit better predictions than axial stresses. This is for structural steel S690. And similarly, we taken another material, stainless steel. Here are the original predictions from classical critical distances. Here are the predictions from modified approach. Here you can see that the predictions are not so good for blunt notches. They are good, but for sharper notches, they are quite conservative. When we compare this strain energy density approach with the approach using axial stresses, you can see that in this case, in the case of this material, the predictions made by axial stresses provide better results. So let me conclude. We have used the critical distances for fatigue lifetime predictions of notch specimens. The critical distances were determined from experimental fatigue data of smooth and calibration notch specimens and based on strain energy density. When we use critical distances as they are, they lead to quite unsatisfactory results. So this modification of prediction distance was used, and this modification leads to better results. Nevertheless, the predictions based on strain energy density and axial stresses were compared. Sometimes is better the approach using SED, sometimes it is better to use axial stresses, so further investigation is needed. Thank you for your attention.